Hello, this next video in a playlist that I'm calling Probability Measure, and in this video we're going to look at an outer measure and define it. And two background videos, BV1 and BV2, where we extend a probability measure from a field to a slightly larger class of sets, and we then extend that probability measure onto all subsets of omega, but we learned that we lost the property that it's a probability measure. And so the video after this, we're going to knock back that requirement of all subsets of omega to some sort of smaller subset. Now, the definition of an outer measure on omega is a non-negative extended real value set function lambda on the class of all subsets of omega satisfying these three properties. The lambda of the empty set is 0, so the measure of the empty set is 0, right? And that's the whole non-negative part. A is a subset of B, implies that the measure of A is less than or equal to the measure of B. That's monotonicity. And then the measure of this infinite union is less than or equal to the sum of the measures of the sets AN. This is called countable subadditivity. If the set function lambda satisfies these three properties, then it's an outer measure. Now, let's prove that the extension that we did in BV2 is an outer measure. So the set function, the theorem, the set function mu star from BV2 is an outer measure on omega. Now, as a reminder, this is just a brief reminder, that for every subset A of omega, we defined that extension, mu star A, as the infimum of all measures such that G is in script G and G is a cover of A. So A is a subset of G. And we look at the measure of all those sets and then take the smallest, and then that's the new measure. That's how we're extending the measure mu. Mu and G, script G, are defined in BV1. So here's a little illustration of what we're doing. So we have omega, we have a field on omega, and we have a probability measure on that field. Now, fields behave so nicely, and it's so easy to develop structure on a field. But to the probability measure, to extend it on larger and larger sets, it's not always straightforward, and it may not be unique. Actually, it's not unique. So we have to develop this rich structure to show that extension can be unique. So anyway, we take this probability measure and extend it to a probability measure on G, and then we extend that probability measure onto all subsets of omega, and that's what mu star is. But we lost the property that it was a probability measure. We extended it onto too large of a set. And so actually the next video, we're going to knock back that requirement of all sets and have it a smaller set. So to prove A, that it's an outer measure, we need to show that the measure of the empty set is 0. Now, we do know that the empty set is in this field F, and we've proved in BV1 and BV2 that this measure restricted to G is equal to mu, and then mu and P are equal when we restrict the sets to F. So if a set is in F, all three of these measures are equal. And so since the empty set is in F, the probability of the empty set is equal to the mu of the empty set, which is equal to mu star of the empty set, which is 0. And that was part 1 of that it's a measure. Now in part B, to prove it, property B of the measure, outer measure, this follows 100% from background video 2, lemma 3C, that if we have an A, a subset of B, then the measures are inequality. So the measure of A is less than or equal to the measure of B. That's a direct proof of in here. Now, to show that it's countably subadditive, In background video 2, lemma 3b, we proved this relationship, that the mu star of the union plus mu star of the intersections less than or equal to the individual measures, mu star A plus mu star B. So if we have a sequence, also this is in background video 2, lemma 3d, we showed that if we have an increasing sets an that limit to A, then the measure of an limits to the measure of A. That was proved in this lemma. So if we have the measure of A, which is equal to the measure of this limit, right, which is equal to this, and this going from here to here is what we proved, right? This is A, and then here if we take the limit inside it, we get this. But mu star is less than or equal to this, right? So if this union is here, and this is non-negative, so if we delete it, then this is always less than or equal to the sum, and that's what we have here. And that's what we want to show. So mu star is an outer measure on omega. And that's all I have for this video. So I hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.